Hello, everyone. Good morning. It's really a pleasure for me to be here today giving this first lecture. So thanks, Ray, and the organizers for inviting me here. And today I'm going to be talking about Jupiter, mostly its interior, and the things that we learned since we have the Juno mission out there. So since this is the very first talk, and even though I know everyone here knows a lot about planets, I just want to say why it's important to study giant planets. Well, the thing is that these planets are the first ones to form in a planetary system, and that's why they have very valuable information in their interiors and their atmospheres to understand how these systems form and how they evolve. In the case of our solar system, of course, we have 4 giant planets. Mostly, I would say Jupiter and Saturn had a huge influence. And the thing is that we want to know more about them, not only because they were the first planets to form, but also because they are so big, they had a huge dynamical influence on the smaller bodies in the system as well. So it's really important for us to understand the history of our solar system to know more about how these planets form and evolve. So this is why, of course, we want to know more about Jupiter. This is the biggest planet in our system, and it had a huge influence. And we want to know much more about it. Now, Jupiter is, as I said, the biggest one, is the closest giant to the Earth. And there were many missions that went there. We had the Pioneers, the Voyagers, the Galileo probe that actually entered into the atmosphere of Jupiter. We had flybys of other missions like Cassini did a flyby, New Horizons also passed by. We can see Jupiter with the naked eye. And we can also observe it with very, very small telescopes. So there is a lot of information that we have for these planets, especially if we compare with exoplanets, for example. But still, there are very key things about Jupiter that we don't know. And the ones I'm more interested in, and the ones I will be talking during this talk, is mostly, first of all, what is Jupiter made of? And we know it's mostly hydrogen and helium, but we don't know exactly the amount of heavy elements in the interior of the planet. And this is, of course, very important if we want to understand how and where it formed and how it evolved. And also related to this, I want to know how these heavy elements are distributed in the planet. Does it have a core or not? Which is the structure? Where are these heavies accommodated in the different layers within the planet? Which is the relation between the atmosphere and the interior? Are there some things that we can say when looking at the atmosphere to infer the interior structure? These are all questions that I want to know, and of course will help us not only to understand our solar system, but in the future, if we think that planet formation is a general process, we might try to understand exoplanets using these models as well. So that's why I really want to know these things. And even though, let me first give you a spoiler, I'm not going to give you a definitive answer on this because it's a very complex problem, but we are learning many, many, many things about Jupiter these days. Now, just to give you an idea of why we really needed another mission to Jupiter, let me first say what the things that we knew before Juno arrived to Jupiter. And this is a classical interior model of Jupiter that we used to use. There are other alternative models, but many people was using this one, where Jupiter had an outer atmosphere, mainly made by molecular hydrogen and helium. As I said, it also has heavies, but they are a tiny percentage of the atmosphere. Then we had an inner envelope, mainly made by metallic hydrogen. If you see, hydrogen has a phase transition. It does not behave as a mass molecular gas when we have very high pressures. And also helium. And helium is, the abundance of helium in this layer is not the same one as this one. And I'm going to be coming back to this later during the talk. I also put there a core, even though, as many of you maybe heard, there was a thing with the core of Jupiter, that we really didn't know if Jupiter had a core, because it was possible to actually fit all the observational constraints with no core at all, just diluting all the heavy elements in the envelope of the planet. And then we were also able to reproduce the observables that we had. So then this was a big question, because it's definitely not the same if the planet has a core or if it doesn't, especially for formation scenarios. And we also had a huge dispersion in the rest of the heavy elements. There were some models where we had very few heavy elements here and a big core. Some others where we had no core, everything was diluted. There were also some models that didn't have this classical structure, but where they have like stairs, like the model that Jeremy LeConte introduced a few years ago. And then if you believe that, there were many, many more heavy elements that you could put here. So there were huge uncertainties. And just to show you an example, this is a figure of a paper I made a few years ago, where I'm showing here the mass of heavy elements in the envelope and the core mass. And you can see results depending on the equation of state that we were using. This is a bit outdated. There are new equations of state now that are not included here. So this is just for you to have an idea of the state of the art before Juno arrived to Jupiter. So you can see that there were big differences. For example, we have like either a very big core and a small amount of heavy elements in the envelope, or even zero core and the rest of the material included in the envelope itself. So we needed to improve two things. First, we needed better methods, better numerical techniques, a better model for the interior of the planet. And we also needed to have better constraints, better observations. And for that reason, we needed a new mission. And we sent Juno out there. So I'm going to say a few things about the mission, just in case you haven't heard about it. Juno is a NASA mission. It was launched in 2011, and it arrived to Jupiter in 2016. So it's been there for 3 years now. And it's not only doing gravity science, that is what I'm very interested in, but it's also doing other great science. He's measuring the magnetic field of Jupiter, the auroras, and also doing atmospheric measurements that I hope we will be hearing more about that in the next years. So it also has a very nice camera. And if you haven't seen so far pictures of Jupiter, I'm putting here some of them because they are just super beautiful and I had to show them. So this is a time lapse that was made by Sean Doran, that is actually a citizen scientist, where you can go to the website of Juno and download the raw images, play around with them and upload them again. And this is an example of this. So this is real Jupiter. What Sean did was to change a bit the colors, to change the contrast. And in this way, he got like the very nice definition of different features. But this is real Jupiter, before you ask me. It's not that the colors are painted or anything. So I think this is amazing. We didn't have pictures of Jupiter like these ones before. And that's why I wanted to show them to you, even though they are not adding to the science I'm going to be talking about the rest of the talk, but I think they are really beautiful. And I have a few more, just one more slide of this. Here you can even see the cloud structures. You can see the turbulence that Jupiter has, like this one here as well. And these are, again, just my favorite. You can just go to the website and check all of them. So we also have seen some, like all these patterns. We haven't seen those before. The thing is that the spacecraft has a very elliptical orbit. And in the perijove, it's 4,000 kilometers above the clouds of Jupiter. And that's why we have these very nice images, because it's passing very close to the planet. We also could see the pole of Jupiter that we've never seen like this before. And well, you can see that the pole is it looks very different than the rest of the planet. It has all these cyclones around. It also has this bluish color that I don't think we've seen in Jupiter before, at least I haven't. And since I'm showing pictures of the pole, I have this very last one that is not on visible, but is on the infrared, and where we can see here the pole and all the cyclones around it very, very clearly. I think this is one of the best images we have of the pole of Jupiter. Okay, now let me go back, not to the nice images, but also the data that is actually as good as the images. And the thing is that to do interior models, we usually use two constraints. On the one hand, we use the gravity field of Jupiter. This really is what we use to make our interior models. And on the other hand, we also use the information we have for the atmosphere. So I will be saying a few things about both. First, on the gravity field, we can write the gravitational potential of Jupiter in this form, where these are the Legendre polynomials, and these are the gravity harmonics. The harmonics that I wrote down here are very relevant for two reasons. First, they give us information on the density distribution in the interior of the planet. And this is what we want to know. We want to know how the material is distributed in the interior. And second, because the observations are expressed in these gravity harmonics. So then this is what we get from the observations. And that's why they are very relevant. And you will be hearing about this during the rest of the talk. So pay attention. We have infinite harmonics. We don't have measurement of all of them. So here is a cartoon also showing the relevance of each of them to give us information on the interior of the planet. So if here we have the core and here we have the atmosphere, you can see that the low order J's, J2, J4, up to J6, I would say, give us information on the internal structure as well as the atmosphere. If we go to higher and higher order J's, then they give us less information on the interior and more information on the atmosphere. So depending what we want to study, which J's we use. It's not that if we have measurements of all of them, we will know more about the deep interior, because actually when we have higher and higher order, we know more about this outer part. So this is kind of a summary of this. If we look at the low order J's, we can study better the internal structure, what I will call during this talk the static components. And if we look at high order J's, then we can study more the deep atmospheric dynamics of the planet. Now, we have other J's. So far, I've been talking about the even, but we also have the odd J's. And the reason why we usually don't hear more about these ones is because if the planet is actually hemispherically symmetric, then these ones are 0 for symmetry. And usually the measurements that we had were not, they didn't have the sensitivity enough to measure these things, and we didn't have odd J's for any of the giants. But now we could measure them with Juno. We do have measurements of the odd J's, and this implies that the planet is not symmetric in both hemispheres. So these J's are actually very important because they give us direct information of the atmosphere. Jupiter rotates in less than 10 hours, so it's a very fast rotator. The interior, we would expect that it rotates as a rigid body and kind of is well mixed. So then the thing is that if we have any asymmetries in both hemispheres, they are probably coming from the atmosphere. And we also made something, is not the nice cartoon I showed before, but this is from a paper that was actually not published yet, so don't post anything like this. So the thing is that here is the contribution of the odd J's to the internal structure. Similar figure as I showed for the even J's, but for the odd. And here what you can see is that if you look at this number, the odd J's are only giving us contribution in the outer 8% of the radius only. So then all the gravity signals that we are getting from these ones are coming from the outer atmosphere. So they are really a window to look at the deep atmosphere of Jupiter. And I will be again coming back to this. Now, let me show you what we had before Juno and what we have now. So before Juno, we had measurements from the Pioneers, the Voyagers. The way that we do this is analyzing the trajectory of the spacecraft around the planet, and the anomalies are due to anomalies in the gravity field. So then this is the information that we had before Juno. Now, we also have J8, we have J10. Here is J12, but this is the uncertainty, so I don't think we can use J12. Let's say that we have up to J10. But we also have, as I said, measurements of the odd J's. So this is all new that we had in the last 3 years, and a bit less, I would say, because this was published last year, actually. So then you can see all these red points are new information, and it's much more than what we had before. So this allows us to study other things that we couldn't really study before because we just didn't have enough information. Now we are also having very much better accuracy. So then here I'm showing J4 and J6, mostly because this is what was very important for the interior models. And here what you can see is this point with very large error bars. That was everything that we had using Pioneer and Voyager data. Now, there were, as I said at the beginning, other missions that also went to Jupiter. We had the Galileo probe, we had Cassini that made a flyby. If we add that information here, this is what we get. So you can see that this is a much better approximation than what we had before. And of course, it helped a lot for us doing interior models. Now, after only one orbit of Juno, like the very first orbit, this is what we got. And the thing is that Juno has a special orbit that was designed to have better gravity data. And that's why we are getting this such amazing data. And this is the best that we have now. It's not that I forgot the error bars. They are inside here. Is that good, the data that we are getting? And of course, this is really amazing because we are getting to know the planet much better. It also implies some problems because we actually had to update and to work a lot in our interior models to catch up with this amazing information. So we were working a lot during these years trying to use this amazing data as it should be, and we still have a lot of things that needs to be done. So now let me move to the other constraint that we use. On the one hand, we use the gravity data. On the other hand, we use the atmospheric data. And for this, I was just curious and I made this figure where we have the different main carriers of the different elements for different temperatures at 0.1 bar. Okay, so what I wanted to know is this. If I want to know which is the elemental abundance of carbon, which element should I look at? That's why I made this figure. So then you can see that depending on the temperature, there are different relevant elements. If we go to the temperatures that we have in Jupiter, this is like here. So if we want to know the carbon abundance, we look at methane. If we want to see the nitrogen, we look at NH3. If we want to see oxygen, we look at water. If we want to see sulfur, we see H2S and phosphorus CH3. This changes a bit if we go to exoplanet regimes. Because if we go to hotter temperatures, some of these are not the main carriers of the elements. And for example, for hotter planets, instead of methane, we look at CO. And also the water is a bit tricky. And this was, by the way, I was checking these. These are fuzzy limits. And of course, this depends on the main composition. This is for solar composition. And also this was for disequilibrium chemistry. So there are some things that might change here, but this gives us a broader idea. And I'm losing my thing. Okay. There we go. Okay, so coming back to Jupiter, this is what we are interested in. And let me move forward. And this is what we have. So here I'm showing the different elements for which we have abundances measured. And here are the elemental abundances compared to the protosun, meaning that if the abundance is 1, this will be the same one as the protosun. This figure was made like this by actually Surjit Latreya in a very nice paper that he published in 2016. And because we want to know how enriched are the atmospheres of the planets in our solar system compared to the protosun, because they form from the same nebula. And we usually assume that they have the same composition. Even when we work with the exoplanets, the first assumption is to say, okay, they might have solar composition or the same composition as their stars. But if we look at the planets in our solar system, we see that that is not the case. They are actually enriched, all of them, compared to the protosun. And there are some other peculiarities in this figure. First, you can see that for Jupiter is the planet for which we have much more data. This is because we had this Galileo probe that entered in the atmosphere and made very nice measurements, especially the noble gases that were measured in situ and we cannot get in any other way. So then if we look at hydrogen and neon, you will see that these two are depleted compared to the protosun. And the reason for that is because there is a phase transition of helium in the interior of Jupiter that also happens in the interior of Saturn. And helium demixes from the hydrogen mixture. It kind of forms droplets that trap the neon and rain down. And then we have a depletion of helium and neon in the atmosphere and an overabundance in the interior. So this is really an important constraint for us doing interior models. Now, if we look at the other elements, for example, there is a peculiarity here. And if you look at oxygen, we don't have measurement of oxygen for any of the giant planets in the solar system. We do have one for Jupiter. I'm cheating here. The thing is that we have this measurement of the Galileo probe of water that was very low. It was around here. And what happened is that the probe entered in a dry spot, and that's why we cannot trust that water measurement very well. And we hope really to get that with Juno, but we don't have it now. And the reason why we don't have any water measurement is because all these planets are very cold, and the water is kind of hidden behind clouds of other elements. In the case of Jupiter, we have a lot of ammonia. So then we should pass all that to actually go and see the water. And that's very difficult to do, and we haven't been able to do that so far. Now, other interesting thing is that if we look at Uranus and Neptune, we don't know anything about those planets. We just have one dot here. And just to put this in context, let me show you what we do know about exoplanets, and I'm sure that you all know more about this. So I had to extend this figure to add all the water measurements that we have for exoplanets. And here, of course, this is not entirely correct because I divided by the oxygen abundance of the protosun, and all these planets were formed around different stars, so they probably have different metallicities. So this was just to give an idea of what we have for exoplanets, and we don't have for the solar system. So this is just for context, because I know that there is a lot of exoplanet crowd here. And actually, if I want to see this better, here I put the water mixing ratios and the metallicities of their stars for all the exoplanets for which we have water measurements that are around 20. And here are the masses of these planets as a function of in Jupiter masses. So here it will be around the solar system values, right? Oxygen abundance of the protosun and 0 metallicity. So we are observing quite different, a big dispersion. And we have a lot of information of this already. And in addition to this, for exoplanets, we also have sodium, we have potassium, we have CO, we have helium detected. So we are having a lot of information for these ones. We do know some exoplanets better than what we know Uranus and Neptune. So we really should think about this and try to study those planets better because they are right here. Okay, now we use all of this. We use our gravity data. We use the radius, the mass of the planet, the abundances that we have in the atmosphere, especially helium abundance is very relevant. And in addition, we have a model that explains the interior of the planet, where we assume hydrostatic equilibrium, conservation of mass, energy. The planet, we assume that we have convection inside, although that might also change, and I will be coming back to that again, and this thing is not. Let me leave it there. Okay, so of course, we don't do this only one time. And the reason for this is because this is a degenerate problem. There are many parameters that we don't know, and that different values of them might give us the right answer. So we want to know which are all the possibilities that explain the interior of Jupiter. And for that, we made thousands of models. So we start with some initial parameters. Some of them we know, some of them we don't know. For example, we don't know the mass of the core, but we know the helium abundance in the atmosphere. We also have the heavy elements abundance here, and we kind of say, okay, we trust that all the other measurements that we have are more or less representative, or we can wait to see what the water measurements give us in the future. We have also that we know the helium abundance in the deeper interior, and so on. So we start with these initial parameters. We calculate which is the radius and the days of a planet that has those parameters. And then we compared. Are these ones the same observations that we have? If they are, then we just keep these as a possible solution for the interior of Jupiter. And we run these thousands of times, and we get a bag with all the possible solutions for the interior of the planet. So if we look at where our models lay, then we have here, this is J4, and this is J6. And this is the same figure I showed before, where we have the Voyager and Pioneer point. This is the Galileo and Cassini, and here we have Juno with the first orbit. And well, this one here, I didn't show it before, but this is when we take into account New Horizons data. But apparently there was a problem with the systematic noise in the data that they had, and that's why this point is so far out. So I took it out from the other figure. Now, our models are all these ones here. All this blue represents where all our models lay. And we are not the only ones doing these calculations. So I included here results by Burkhard Militzer and Bill Hubbard, and these are calculations made by Nadine Nettelman. And these are just recent calculations. There were previous calculations made as well on this. So you can see that there is a huge dispersion in the values that we are getting. And Jupiter does not look the same if it's around here or if it's around here. And we want to know which is the difference because we only want these models. So then we were studying which is the main difference between all of these. And we found that there are mainly two parameters that really determine the internal structure. One is the equation of state, and of hydrogen mostly. And believe it or not, we still don't know very well the equation of state of hydrogen, at least not for the conditions in giant planet interiors. So fortunately, there is a lot of people working on this now. There is a new equation of state published this year that kind of agrees much more with the previous one than others, but there are still some uncertainties on this problem. And I'm really happy that there is people working on this because this is a very important thing that we need to solve. The other important parameter is the distribution of heavy elements in the interior. So then in this figure, I'm showing exactly the same thing as before, but now our models, instead of being with that blue area, are all these points here. And the difference, the gradient, means the difference in heavy elements in the atmosphere and the deep interior of the planet. So then what we see here is that this difference is zero when the planet is completely homogeneous, when there is no difference between the heavy elements in the atmosphere and the deeper envelope. And when that happens, we are around here. So you see that Jupiter is definitely not homogeneous. These values here cannot explain the data that we are getting. So we need to have kind of more heavy elements towards the interior of the planet. And this is actually a very important result because it's telling us that the planet is not homogeneous. We need to have something down there. So it kind of rules out the no core scenario that we had before. So then we introduced a new model for Jupiter that is similar to the one I showed you before, in the sense that we have the atmosphere mainly made of molecular hydrogen and helium, the deeper interior of metallic hydrogen and enriched in helium. But I included here another layer that we call the dilute core, that actually is a layer that is highly enriched, where the heavy elements mixed with the hydrogen and helium envelope. And here we have the core itself. So of course, this is one model. There are other alternative models, and if you are interested, I invite you to look, for example, the paper by Debras and Chabrier published this year. But this is one possibility that actually explains the results that we are finding with Juno right now. And we like this much more than the previous one, also because there are some formation models that said that the planet can actually have a dilute core from the formation point of view. Okay, now let me move to the second and final part of my talk, that is talking about another issue, but that is also related to understand the interior of the planet, and is the rotation of Jupiter. In particular, the differential rotation of Jupiter. So when we observe the planet, and we've been doing this since long time ago, we can see that we have these zonal winds. that Jupiter has that some of them go in one direction, some go in the other one. They have different velocities. And we've been observing that since years. The thing is that what we don't know is how deep these winds extend into the planet. And the reason why this is important is because all the models that I showed to you so far are assuming that the planet rotates as a rigid body. And if that is not the case, if these winds extend very deep into the atmosphere, into the planet, then we have to take this into account in our interior calculations. Otherwise, we might be taking wrong results. So we wanted to know more about this. And what we did first was to quantify how big is this. So then again, this is the same figure I showed before, J4, J6, our models, and the Juno data. And here I'm showing the last calculation that we have. And the thing is this. All these models, as I said, are calculated assuming a rigid body. What happens? So if Jupiter rotates indeed as a rigid body, the only good solutions are the ones exactly here. Now, we know that the planet does not rotate as a rigid body. So then if we include this differential rotation, there might be other models around here or here that also explain the data when we take this into account. So then we did an exploration of the extreme. We said, okay, let's assume that these winds extend all the way to the core. Then which models, which ones of all of these actually explain the data if we take that into account? And we found that all of those ones here can actually explain the data in this case. So you see that this again represents a huge error bar for us because these models here can also explain this point in these models here as well. So we needed definitely to quantify this better. Now, do you remember this figure that I showed at the very beginning? Yes, no? You're still waking up? So we have the even harmonics and the odd harmonics. And if you remember, I was telling you that the high order harmonics are the ones that we look at if we are seeing the deep atmospheric dynamics. And I also mentioned that the odd gravity harmonics are only giving us information on the outer part, on the atmosphere of the planet. And as I also said, we didn't have information of these ones or these ones before Juno. We only have it now. So then now we can use this information to actually understand and constrain this differential rotation in the interior of the planet. And that is what we did. So we did that with two different methods. We use on the one hand this information with the even gravity harmonics, and on the other hand, we use the odd gravity harmonics, and we checked if we were finding similar results. So let me first show you what we did with the even J's. This is the first figure, the same one I've been showing so far. J4, J6, all these points are our interior models. For now, ignore these squares here. And that yellow, tiny yellow point is the Juno point that actually is zoomed in there. No surprises here. Now, let me show you what happens when we actually do the same thing for higher order J's. This is for J6, J6, and J8. And again, here are all our interior models. That is the Juno data. You can see it zoom in here, our interior models and the Juno data. Just don't look at the squares. And now I want you to tell me, is there any model that explains the data? Not even one of all the models are down here. The data is up here. We tried many different things. We tried with other models. There are also calculations like Burkhardt-Milits are here. We tried different equations of the state. We tried all the different things that we could think of, and there was no way of explaining the data. And of course, the reason for this is because we are looking at high order J's, and differential rotation starts to be important, and we have to take that into account. And the same thing happens if we go to even higher J's, where here I'm showing J8 and J10, and here are our models. And now the error bars are a bit larger, and it looks like we actually can explain them, but it's like fuzzy. So then the thing is that we said, okay, which is the depth of these winds that will actually allow us to explain this? And our exploration showed that if we have winds as deep as 3,000 kilometers, then we are actually able to explain all the J's with our calculations. So then this is really great. We could put some constraints on the differential rotation of Jupiter for the first time. And now let me show you what we found with the odd J's. And this is a much more trustworthy method, I have to say, because the odd J's directly are related to the atmospheric dynamics. They have no influence on, the interior has no influence on this. And this figure is a nice figure calculated actually by Yochai Kaspi, and all of these are his models, where he was studying the circulation of these winds. And then he calculated which would be the value of the different odd J's depending on the depth of these winds. So if these winds are very shallow, if they don't go very deep into the planet, then there is a very little mass involved in the winds, and then the gravity signal is going to be small. So therefore, we will be around here. Now, if the winds go deeper into the planet, and then there is more mass involved in the winds, there is a larger gravity signal, and that's why we have a larger values here. So he made this figure theoretically, and now we can put here the measurements that we have. And what you can see is that all the measurements overlap with the theoretical calculations at more or less the same place, and that is also between 1,000 and 3,000 kilometers. So then with two independent calculations, we reached the same result, that the winds that we observe in Jupiter extend up to 3,000 kilometers. And this number might not telling you much. This is around 4% of the radius of the planet. And it involves between 3 and 4 Earth masses of material going around in these winds. And that's why it depends on the point of view. From the interior point of view, the rest of the planet is a rigid body, so 96% of the radius is rigid body. It's fine. It's not a terrible approximation, the one we were making. Now, if we look at this from the perspective of the atmospheric dynamics, this is a lot. This is 4% of the radius. It's around 3 Earth masses of material moving around in those winds. So it really is it's something, I think. And we can constrain this, as I said, for the first time. We also did a similar analysis for Saturn. I'm not going to show it here because I wanted to focus on Jupiter and the Juno mission, but if you are interested, we can talk about that later. So one last thing that I want to say is, okay, why this happens? And we are trying to understand what is actually stopping this flow. And now there are different things that we have to take into account. And a nice thing of this period of the Juno mission is that now we have to start talking with the other teams and trying to put all the puzzle pieces together. One of the big puzzle pieces that we have to combine definitely with these interior models is the magnetic field, that we actually have very good measurements of the magnetic field of Jupiter that we didn't have before. And that might be playing a big role here. So what I'm showing here is, again, the depth of these winds. And this black one is the profile, the wind profile that actually was used in the previous calculations, because that's another question, right? We are measuring the winds very up in the atmosphere. How is the form, the shape of these winds when we go deeper? So in this case, we were assuming an exponential decay that you can see it here. And these blue are new estimations calculated by Karen Duer, where she's having this magnetic field into account, and we are trying to improve this. And what you can see here in the dashed lines is the electrical conductivity in the interior of Jupiter, made by models mostly by Cao. So what you can see is that the electrical conductivity increases suddenly when our winds stop. So we think that actually there is a magnetic drag playing a role there and stopping the flow, and that's why then we have a rigid body rotation. But we are just trying to understand it right now. Okay, so I was much faster than I expected, actually. I just want to show this nice animation just to give you a more visual idea of these effects. And this is from a press release that NASA made for the results of our papers. And you can see here the flows, the zonal winds that I was talking about, and that they extend up to around 4% of the radius of the planet. And in the deeper parts, the planet rotates as a rigid body. So I think this is a nice way of visualizing this problem. And that's why I wanted to show it to you. Now, let me just go to the take-home messages of this talk. And the thing, first of all, is that we had much larger, great improvement in the gravity data that we have with Juno. And I think this is really the best. We don't have this kind of data for the other giant planets. We do have very good data for Saturn. For Saturn, we also have some extra information that came from seismology, but we don't have such a good gravity data for the other ones. And this is really due to this special orbit that Juno has. We also could learn a bit more about the internal structure, even though I cannot tell you yet which is the mass of the core. And I know you all want to know, because every time I give this talk, the people is like, well, but you didn't tell us the mass of the core. And the thing is that is a very complex problem. And now that we have this dilute core, we are adding extra layers of complication, let's say, that we didn't have before. Because now we have other questions, like how steep is the gradient of the composition there, how that might affect the way that we are transporting energy, and therefore the amount of heavy elements that we can put, which is actually the amount of heavies there and how they increase in this dilute core. So there are like many, many new questions that we need to solve and discuss what we actually call a core, if it's only the tiny part that has 100% heavy elements, or if this fuzzy dilute core also counts as a core from the formation point of view. So we need to have some discussions to actually understand this a bit more, and of course study this better before we can give a definitive answer. But something that we can say is that we need to have something down there. There is definitely a need for a larger amount of heavies deep down to explain the observations. There are, we could also constrain the differential rotation in the planet, and this goes approximately up to 3,000 kilometers. And of course, this is also something that we have to put in the interior models, because even though the rigid body is not such a bad approximation, we still need to have this into account if we want to get more accurate results. And especially because now we know how deep they go, so we need to take this into account. And finally, but not least, I haven't done all of this by myself. There is a very nice interior working group in Juno, and all of them are here. And now from this year, we also have Jonathan Fortney and Nadine Nettelman joining us, so they will be here in the next talk. And here we have the whole Juno team, where you can see on this side the engineers and this side all the scientists that actually made this very nice mission possible. And thank you for your attention. There.
We're good. Yes. Okay. Amazing. Yasmina, you're leading the way. Hope everybody will be 5 minutes early on their talk, like you. So we do have a lot of time for questions about Juno.
I wanted to make your life easier the rest of the session.
Exactly. Any questions?
So for the magnetic drag, there's 3,000 or somewhere between 1,000 and 3,000 kilometers deep part on Jupiter. What's the pressure and temperature there? I'm trying to reconcile this with like hot Jupiters and magnetic drag there.
Oh, the temperatures, I don't remember. The pressure is 0.1 megabars. So it's a lot. The temperature, I don't remember. I can check and give you that number later. Yeah, I remember, well, the temperature is very deep in the core at 20,000 K, but in the core, like there is less. I'll check.
Okay, we'll go. Good job.
Yeah, would it be true to say or not that the Juno results would be consistent with having deep equatorial jets, say from -20 to +20, with shallower extratropical and high latitude jets?
What do you mean, like deep, the jets that we observe?
Suppose the jets, jets that you observe, perhaps that Perhaps they're only deep in the equatorial regions. And
Okay, yeah.
higher latitudes.
I see. So right now we made like a global analysis of this, but you are right that we now have to go to specific parts of the planet. Also, we are interested in the Great Red Spot, for example, to see how deep it goes, but we haven't done that yet, like specific parts. It's something that we need to do. Yeah.
It's running to you.
Thank you. From the outside, it's all gravity, but you presented the model fitting to the odd and even harmonics as quote unquote independent. How within the team did that sort of arise? Did somebody say, I'll do the odd ones, you do the even ones, and then we'll blend them together
the team
later?
interior dynamics.
Yeah. How did the process work?
So we are around between 20 and 30, I would say. I don't know exactly the number, but half the team is doing the analysis of the observations themselves, and the other half, we are doing the interior models. Within the interior models, so far we had 2 independent teams. Now, as I said, Jonathan and Nadine are also joining, but it was Tristan and me on the one side, and Burkhard Militzer and Bill Hubbard and their team. So we were doing independent interior models and trying to discuss and get a consensus between us. And with the observations, it was more or less the same. There were 2 teams. There was the JPL team, led by Bill Faulkner, and there was people from Italy, led by Luciano Jess, and they were both doing independent calculations and then trying to discuss. I heard endless discussions about the error bars, and you can see that they are tiny, but they really wanted to have the consensus on that. So
was submission of the various publications coordinated, or?
Yes,
okay.
yes. We definitely discuss everything and coordinate everything. Yeah.
Right.
Okay. Yes, thanks. Yeah. So I was interested in the data point you put up for the carbon in Uranus, and I presume that's from spectroscopic measurements of the outer part of the atmosphere. Do we have any constraints from the bulk density of Uranus on how that carbon abundance relates to the bulk? I'm wondering, there's always this question of how the outer atmosphere that you can see relates to bulk, the interior composition, because for the exoplanets, we will have bulk density and we'll have outer atmosphere, and putting those pieces together is always a tough thing.
Yeah, I definitely agree. I'm also doing exoplanets, so that's why I'm also interested in this problem. The thing with Uranus and Neptune is that we also have very poor information on the gravity as well. Only the Voyager 2 went to those planets. And then we have like only one point with huge error bars. We don't even have J6. We just have J2 and J4. So then we have this gravity data doesn't allow us to make such detailed models as we are doing here and find a relation on the heavy elements. So I don't think we do have an answer, or at least I don't really know an answer for that. I haven't been doing a lot of interior models on that. So, but that is definitely something important to look at. And that's also why I'm saying that we need to observe them more, because they are here. They might give us clues of how exoplanets work, and we don't know a lot about them.
Yeah, so I was wondering if it's on that.
Step it down.
And wait for 10 seconds. Hello? There we go. Could you comment on the possibilities for constraining the temporal evolution of the core dilution? Because it seems like you could have, thinking about n-member scenarios, you could have a core forming and then stuff diffusing out, or you might have a later delivery of heavies, which then puts it in place, and it's not really significantly evolving subsequently from formation. So, and clearly that there's big implications in terms of constraining formation scenarios between the two. Do you want to comment on prospects for constraining that?
Yeah, sure. So there are very nice models by Alona Bazan actually doing evolution models of Jupiter considering compositional gradients. And her results show that actually it's possible to have. So she starts the planet with compositional gradients, and she looks at how these evolve and if it's possible to maintain that from formation to what we observe today. And she found that indeed it's possible to just maintain this dilute core from the formation point of view. So there might be two possibilities. One is that when we were forming the planet and we were accreting gas and solids at the same time, then this kind of dissolves and enriched like this part around the core itself, something like that. But this is, again, being studied. I think that there are a few papers that are dealing with this as far as I know. The other possibility is that this happened later on, and it's not a dilute core, but an eroded core. So then you had your core forming, and that was the erosion during the evolution could mix the heavy elements there. That's the other possibility. But I know that Ravid Held with Tristan were analyzing that, and apparently it's a very inefficient process. So the erosion, it might be, the other scenario might be a bit more favorable, but we, again, need to study all of these more.
Thanks.
There's two more.
All right.
Okay, Adam is on your way.
Yeah, got a good trajectory. Okay.
A great talk. I had a follow-up comment related to the question that I guess that was Jeff Vallis. About the the relative sort of low equatorial versus high equatorial. The dominant sort of lack of symmetry around the equator and the cloud top zonal winds is that huge zonal jet at sort of 23 degrees latitude, which lacks a counterpart in the other hemisphere, and is of course outside the equatorial jet. And then, and so that would sort of suggest that the odd harmonics are actually sensing. When one sort of quotes a number of 3,000 kilometers, it's not just inside the equatorial jet. And Yochai actually did an analysis where he looked at the latitude variation of this parameter h. And that analysis showed that at low latitudes, the thickness is somewhat larger than at high latitudes. But I specifically asked him the exact question that you asked, whether it's possible to have all of the sort of deep, the signature of the harmonics inside just an equatorial jet that cuts across the planet, and have the high latitude jets all die out at a very shallow depth. And the answer is no, as far as I understand. I don't know if that would agree with what you think, but you start early.
Yeah, exactly. Yes, thanks for the comment. Yes,
thank you.
Yeah.
The slot's 15 minutes.
Yeah. 70.
No, this is an interesting question to ask just because you never know. But will the microwave radiometer be at all helpful with constraining the circulation of the deep interior, or is it just going to be entirely too shallow for the problems that have been interesting you? Because I know we're supposed to go to about 100 bar, but that's probably, Kevin, you're talking about 100,000 bar. That seems a little far off.
Yeah, so you gave the question and the answer. So
fair enough.
Yes, so yes, with the microwave we are seeing 100 bars. This is much deeper, but still with the microwave radiometer we hope to have the water abundance at some point, and that will definitely help us here, because the big question, of course, that if this planet formed beyond the snow line, the ices, the water is going to be what represents the heavy element in the interior. So we want to know the water abundance, and we don't have that yet. So yeah, so it will help a lot, but not on that sense, but on others.
Can I have one more question? Anybody still eager to know something from you, Shamila? Well, thanks so much, Shamila. It was really good.